All right, so as we saw last time, this method of initial rate can be quite time consuming, quite tedious. There's kind of a faster way to do it. It's essentially the same way we did it last time. It's just showing less steps. So let's take a look at an example of this. So in this example, we have CHCl3 chloroform combining with Cl2 chlorine gas to form CCl4 carbon tetrachloride and HCl hydrochloric acid. And of course, to determine these rates, we have to do this experimentally. So here's some given data. So we have trial 1, trial 2, trial 3, and then trial 4. And then we're going to change the concentration of our reactants. So our CHCl3 will start off with 0.010, double it. Keep it the same for trial 3, and then double it again for trial 4. And then we have our concentration of Cl2, our other reactant, 0.010. Keep it the same for this one, 0.020, 0.040. And then we measure the rate, which is in terms of molarity per second. Rate is always concentration over time, always concentration over time. It's not necessarily molarity, but most of the time it is. So in this case, let's see, give you some experimental data. Cool. And then the next thing we have to do, same thing as before, is write our rate law. So in this case, rate is going to be equal to K times the concentration of one of our components, CHCl3, to some exponent, times the concentration of the other component, Cl2, to some exponent. And now we want to go ahead and solve for these exponents. So here's M. We want to solve for the exponent that belongs to CHCl3. So we want to pick a trial in which the concentration of CHCl3 is changing, but the concentration of Cl2 is not changing, right? We only want to change one variable at a time. And so that ends up being trial 1 and 2, right? Our concentration of CHCl2 is doubled. This Cl2 stays the same, so we're good there. And then take a look at your rate. What's going on at this rate? To go from 0.035 to 0.069, it is doubled as well. And so we're kind of doing the same thing we did last time, except we're going to skip the step where we cancel everything out. So we're just going to go ahead straight to the part where we write rate of 1 over rate of 2, so 0.0035 over 0.0069 equal to 0.010 over 0.020 up to some exponents. And you can tell that this is 1/2 equals 1/2 to the m, and so it ends up being 1 as well. But you can go ahead and do the math as well, right? This is equal to 1/2. This is equal to 1/2. And so at this point, you should probably be able to tell that m is going to be equal to 1, right? In order for 1/2 to equal to 1/2, it needs to be 1. But if you want, you can go ahead and do the log method as well. So you see we calculated m here. It's essentially the same method we did last time. We're just showing less steps, less of the canceling out of stuff. And then we need to find the concentration or the value of n here. So we want to pick a trial in which the concentration of Cl2 changes, but the concentration of CHCl3 does not. And if you look carefully, you would identify trials 2 and 3 to be that, right? The concentration of CHCl3 does not change. This gets doubled. And then something, yeah, it's probably not quick enough to do this math here in your head, so let's go ahead and write it out. Again, we're going to skip the step of showing how things cancel out because we know they cancel out. So we'll put the rate of 2 over the rate of 3, so 0.0069 over 0.0098 is equal to 0.010 over 0.020 to the n. And then if you want to go ahead and type that into your calculator, you get 1.4 over here, which is a little funky. And then you get kind of 1/2 to the m. And so this one you cannot do or to the n. This one you cannot do in your head. You have to do the long way. So we're going to take the log of both sides. And then we're going to put this n out in front because we are allowed to do that. And then we divide both sides by log of 1/2. Oh, what's my bad? This value is not 1.4. My bad. Let's check this out. 0.0069.0098. Should be 0.70. Cool. That makes more sense. All right, and then we type that in our calculator. Log of 0.7 divided by log of 1/2. And we get 0.5 or 1/2. So as you can see, these orders do not have to be whole numbers. They can be 1/2s and whatnot. And so now we've got our N and our M. So let me just go ahead, kind of partition this over here. And so we can rewrite our rate. Rate is equal to K, concentration of, what was the CHCl3, up to the 1, so we can just leave it there, times the concentration of Cl2 up to the 1/2. And now we need to solve for K, so we can pick any trials. I'm always lazy, so I always just pick the first set of data. So we're going to plug in 0.1 for each of these concentrations, and then the 0.0035 for the rate. The rate has units of molarity per second is equal to K times 0.1 molar times 0.1 molar to the 1/2. Divide both sides by this 0.1 molar times this 0.1 molar to the 1/2. And then we'll get K by itself. You can see that this molar is going to cancel out with this molar. And then you can just plug in the rest of this stuff into your calculator. You should get 3.5. And then think about the units. This is 1/2 underneath, so it's m to the negative 1/2. And then the seconds is also in the denominator, so seconds minus 1. So you can see K has some pretty funky units. And so then we can rewrite the overall rate loss. So rate is equal to 3.5 molar to the negative 1/2, seconds to the negative 1/2, times the concentration of CHCl3 times the concentration of Cl2 to the 1/2, and this is our final answer. Honestly, the only way to get good at this stuff is to just practice, 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 and then you'll find your own little shortcuts and see what works and what doesn't work.